Okay, good morning everyone, and welcome to our TEWI-Kolloquium on Content-Gnostic bitrate ladder prediction for adaptive streaming. It's my pleasure to welcome and introduce you Angeliki Katsenou, hopefully I pronounced this correctly. She is with the University of Bristol already for quite some time. But she obtained her PhD degree from the Department of Computer Science and Engineering at the University of Ionia in Greece, and is now in Bristol working on projects related to perceptual video analysis, video compression, image video quality, and resource allocation for video communication system. And this talk is a very hot topic now for, I think, HTTP adaptive streaming systems and researchers working in this domain, and I'm very happy to have her here in this environment. And please go ahead and start your presentation. And I think it's a good idea to have the questions then at the end. Thank you.
Sure. Thank you very much, Christian. So as Christian said, I have been working with Bristol for my postdoc since 2015. And I have been working generally on video compression topics, a bit on video transmission, and on video quality topics as well. So this particular seminar is about a work we have been doing in collaboration with Netflix. And it is on, the title is Content-Gnostic, bitrate ladder prediction for adaptive video streaming. I'm quite familiar that your group has also been working on very similar topics. And I have been following your work as well. So it's quite a pleasure for me to be sharing this work with you at the moment. So my structure is going to be quite simple. I'm just going to give you the motivation behind this work, a bit of information on my views about the relation between compression and content features. Then I'm going to go through the proposed framework that I have started developing last year and I'm also currently working on. And then I'm going to share with you a few results. I'm going to share with you results that have already been published. I'm saving a few for future work. And then I'm going to share with you also some thoughts about my future directions. So I'm using two monitors, so it's splitting the frame, so you might look away, but I'm actually looking at my actual screen. So as you all know, Cisco, like 2 years ago, reported that 80% of the data traffic would be concerned about video. And to be honest, this figure we are expecting also to reach quite earlier because of the coronavirus, and as with using a statement from the founder and CEO of Zoom Technologies. So Zoom, which is one of the platforms, the platform we are using now, but also one of the platforms that a lot of people around the globe have engaged, either for educational purposes or for day-to-day business. So they say that at the end of December, they had approximately 10 million users. And then in March, when most of the globe was in lockdown, they reached about 200 million participants. So this increase of people using video services has been huge. And I'm sure there are other reports, other companies reporting around very, very similar figures. So another issue we have with video streaming is that every user has their own different specifications, which means that we have to find the best, let's say, version of a video to encode in order to send it to people's phones, or we have to find the best encoding solution so that people can really enjoy a movie at their 65-inch display at home. or that other people in other parts of the world with low bandwidths, they can equally get a decent version of their favorite movie or the video they want to share or the video call they want to make. So in order to do that, the video providers, of course, employ adaptive streaming to address all these user specifications. In order to do that, from the side of the video providers, we have to be able, let's say, to identify these unique user specifications and also find the best encoding solution for that. However, all these, of course, requires a huge amount of computations in order to meet all the user requirements and all user specifications. And this has a huge impact on time, cost, and energy, of course, as the SHIFT project has reported. So it was quite impressive when I found these statistics from the SHIFT project, where they are saying that the amount of CO2 emissions that the ICT technologies actually emit is equivalent to those from flights. And although we have, in many countries, there has been a movement on making people feel a bit bad about using planes. On the other hand, we need to understand that every choice we do in everyday life, and also the amount of communication technologies we use, it has also a direct impact in the environment. So as engineers, I think we have the responsibility to try to find the best solution that will, let's say, satisfy the need of an engineer to find the smartest and more efficient solution, but also at the same time be a bit more responsible in terms of how we use ICT technologies. All videos, of course, have very different characteristics, and that adds another dimension of complexity in our problem, that each one of these 100 videos, short video clips I'm showing to you right now, has a completely different rate distortion performance. Traditionally, a fixed encoding ladder was suggested, like the one I'm showing here in table 1, where for each video you would use a very specific bitrate in order to meet the network bandwidth and match the network bandwidth. You would have specific profiles depending on the network statistics and so on. But of course, if we extract the rate distortion curves from these 100 videos at 3 different resolutions, at 4K resolution, at full HD resolution, and at HD resolution, as you can see, the plane of the curves is quite extended, which means that there is a lot of diversity in the rate distortion performance of those different curves. Of course, there have been efforts that have tried to address this, that I'm going to go through. But one is for sure, one bitrate ladder does not fit all. One bitrate ladder does not guarantee that the delivered video quality will be satisfactory for the end user. So, of course, starting from, I'm sorry, I skipped that. So, of course, as I said, starting from a fixed rate ladder, we moved at some point in a per title bitrate ladder, and Netflix, I think, was one of the first companies who have worked and have suggested something like that around 2015. So instead of having a default bitrate ladder, as you can see here, for each resolution, they have suggested a per title bitrate ladder, So for each different movie or for each different video, or chunk of video, they suggested a different bitrate ladder. This approach has been followed by other companies like Bitmoven and Max and Cambria and many other companies that I'm not referring to here. And this has also been extended into let's say, higher resolution bitrate ladder into going into a per shot bitrate ladder production. So the way other companies have tried to approach this is either by doing the traditional brute force method, which means take one video and downscale it in every resolution you would like to deliver to, encode that video in all the range of QPs, let's say, with an increment of 1, and then upscale it, compute the PSNR or the VMAF or any other quality metric, and then build the convex hull, and from that derive the bitrate ladder. So that is the brute force approach. There have been other approaches that have been based on trying to estimate the encoding complexity by doing, for example, a few encodes and then trying to estimate how much complexity that has, and then trying to provide a solution on that. And another popular approach has been to take a higher increment of quantization levels, let's say a step of 5, and then construct the RD curves by using interpolation. And then again, finding the convex hull, and based on that, let's say, suggest the bitrate ladder. So my work is actually concerned with the hot question: how can we find the best one? The first question is, how can we find the best bitrate ladder per content, so that we don't have to compromise the quality of experience for any user and for any type of video, no matter how demanding that is in terms of resources? And the other question is, how can we make this process more computationally efficient without, again, degrading the delivered video quality? So ideally, as we discussed, ideally we would have the theoretical solution lies on the convex hull, on the upper convex hull of the rate distortion curves. And then any other solution, like, for example, interpolation-based, they would lie into a more a suboptimal, let's say, curve that, of course, cannot reach this theoretical optimal rate distortion curve, which we would use to build the optimal bitrate ladder. From our end, we decided that we wanted to find a content-gnostic machine learning-based approach that can predict as much as possible and as close as possible to the optimal, that bitrate ladder. So how to do that? We were motivated by our previous work, which related the content features and the compression by extracting from uncompressed content low-level features, very classical spatiotemporal features from some of them from the image processing techniques, like, for example, the gray level called Currents matrix. Some of them adjusted to the video content, like, for example, the normalized cross-correlation between neighboring frames, and other also very known descriptors, spatiotemporal descriptors, like the optical flow. and many more. We have tested that on a big pool of features, and here I'm presenting you just a small number of features. And we found in our previous work that there is, with some feature, there's a strong correlation with encoding statistics. Like for example, the normalized cross-correlation is highly correlated with, let's say, the percentage of intra modes that is being used. Or, for example, that the GLCM contrast is highly correlated with the number of bits that have to be spent in order to encode that, so with the bit rate. And in our previous work also, what we did is we used a combination of those low spatiotemporal features, and we were trying to predict the actual rate distortion curve at a specific resolution of a sequence by using a simplified linear model in the PSNR logarithmic bitrate domain. And that didn't go too bad, so therefore we decided to extend this work and try to reduce it into a more complex problem. So let's assume we have these three resolutions, the 4K resolution, the Full HD, and the HD resolution over, let's say, 100 sequences that I have showed you in the beginning. And if we downscale and then upscale to compute if we downscale to encode and then upscale to compute the quality metrics, we can draw these PSNR log rate curves across these resolutions. So as you can see, and as expected, those curves intersect at different points. They have different behavior. And if we get an instance like the one in figure 6, we can see that a very typical case of intersecting rate distortion curves is that the 4K resolution RD curve intersects with the Full HD, and then the Full HD with the HD. Of course, there are exceptions because those curves, although theoretically they should all look like that, so practically, we have noticed that in some cases, for some sequences, there might be more than one intersections of two resolution, or there might be a couple of cases where, for example, the Full HD curve might be on top of the 4K curve. So the rule of assuming, for example, that we have an ordered monotonic intersection of the curves is not always satisfied. But for our work, we consider these cases as outliers. And so we make the assumption that indeed we have this type of intersection. So when we were trying to formulate the problem, we thought that for starters, it would be easier to define these intersection points by the QP, by the pairs of QPs of the curves that are intersecting. Although the holy grail would be to find directly the bit rate where those two curves meet, we found that was a highly complex problem, and we thought to start by predicting first the QPs. So, sorry. All right. So we define these pairs, these intersecting pairs of QPs, and as you can see, for the resolution in between, we usually have two descriptors. The one is the higher, which is usually a lower QP value, is tagged as QP low FHD. And the lower point here is tagged by QP high FHD. This is just to discriminate those 2 points. We also found that those intersecting QPs, those crossover QPs as we are naming them, they are correlated, and they can be modeled and approximated with a line. The relationship can be approximated with a line. This means that, for example, if I could predict with my features one of the 4 QPs that I showed earlier, I could probably get a good estimation of the rest of the QPs. However, we are in our method, we will try to use the features to estimate each one of the QPs, but again, using this underlying relation between the crossover QPs. The reason you see here these points is because at this point we had a clipping. We assumed the higher QP here was 35, so we have a clipping point, because at this point of at this stage of the research, we assumed a more constrained QP range. So based on these first slides, we defined a framework that is using uncompressed content to extract features. Then it's using offline, it's encoding all the sequences in their downscaled version in order to obtain the ground truth, which means that these theoretical crossover QP points that can help us train the features along with those ground QPs. They can help us train machine learning based models, which we use to predict those crossover QPs. And then when we predict those crossover QPs, we can simply find the bit rates of the the bit rates that define the switching points of the resolutions by doing those simple foreign codes, for example. We could even assume, if our algorithm works well and we have a high accuracy, we could even, for example, only to make 2 encodings for these 3 resolutions and those 2 4QPs. We could make 2 encodes only. And then we would have the switching points, the bit rates of the switching points for the resolution. So that would be a first step of building the bitrate ladder. Of course, we wanted something more complete, so we have extended this method beyond that by fitting the RQ convex hull into a 3rd order polynomial, as you will see, and then using some relations that can give us more detailed relation across different resolutions of the QPs and the bit rate, and also the quality and the bit rate. Then we are able to have the full definition of the RQ convex hulls. We will know the switches of resolutions, and then at that point we can also subsample that convex hull and derive the bitrate ladder. We applied this framework on 2 types of metrics, on PSNR and also VMAF. As you can see, this figure 9, shows the convex hull across a wider range of resolutions for these 2 metrics. And as you can all observe, those convex hulls, they look very different depending on the metric we use. And as you can probably notice, they look very different also on the types of resolution that constitute the convex hulls. For example, when using PSNR, you can see that there is a higher number of 4K points. While, for example, when you use the VMAF metric to predict the bitrate ladder, you might end up having more full HD points than compared to PSNR. That means that those curves, using different metrics, we can build completely different curves. And of course, ideally, we would like to have a huge data set with the perceptual subjective quality rate distortion curve, like MOS rate curves, so that we are able to predict the bitrate ladders based on that. But at the moment, we assume that VMAF, for example, can provide a good approximation, a better approximation than PSNR for this perceptually aware, let's say, bitrate ladder. As I said, the next step was to extend the model, and what we did is we tried to fit different models on the convex hull, and of course it would make sense that the third order degree polynomial would give a better fit to the convex hull, and this has actually worked for both PSNR and VMAF. And that also means that by fitting this third order polynomial, we have, for each one of the sequences, we have 4 parameters that need to be defined in order to have this equation fully defined per video, which also means that we need foreign codes in order to determine those polynomial parameters. After defining this equation, as I said before, we can sample the convex hull and build the bitrate ladder. How are we building the bitrate ladder? We need, of course, a couple of rules for that. So the first step is, of course, to determine an operational bitrate range. So where, for example, the video provider would like, in which range of bitrates the video provider would like to transmit over. And we need then to trim, let's say, the convex hulls in that bitrate range. And then in order to build the bitrate ladder, we need to take some increments of bitrates, and we have employed the simple rule of each bitrate being 2 times the previous one, which in the logarithm space means that an increment of 1 is to be added every time. And then after doing that, we also have applied a quality, some constraints on the quality dimension, and these have to do, one, with the type of quality metric we are using. For example, when we use VMAF, we have this normalized metric, and we know that the maximum value it can assume is 100, which means that any curve is naturally bound by that. But we could also, for example, put some threshold on that and assume that, for example, if the quality is 98 or if the quality is 97, there is no significant difference to the perfect quality. And so we could lower that threshold and trim a bit more that bitrate ladder. And another rule we could apply, and this could be applied also for PSNR, is when we achieve a kind of saturation in our curve, when we have, for example, a curve that is becoming flat after some bitrate or almost flat, we could apply a rule on the slope of the curve, and then we could further trim down the bitrate ladder. This means, of course, that we end up having, for the 2 different quality metrics, we end up having 2 different images, as you can see in figure 10 and 11, of the 2 bitrate ladders. So in the case of PSNR, we can see a very distinct, let's say, image of the different ranks of the bitrate ladder. On the VMAF case, we have a bit of more mixed, let's say, ranks across the different sequences of our data set. And we also notice in this upper area that we seem to have less points than we have at the respective area in PSNR. This means that with the quality constraints we've put on VMAF, we are able, let's say, to reduce the number of steps on the ladder, the number of ranks. And these also rules mean that for different content, we end up having a different number of ranks on the bitrate ladder, which is also a big gain. Since we can reduce the bitrate for specific type of contents, and we can let's say have less. We can provide to the video service provider a recipe with less steps, less encodes at the very end that he has to make. All right, so I'm going to move on a few of the results. As I said, I'm presenting here results that have already been published because I'm submitting very soon another extended version of the paper with the basic elements that I have described before. But I would like to publish those and share with you later on. So for the first part of this work, we have used a subset of the features I presented in the beginning. And the reason for selecting the subset of those features were two. One reason was we wanted to have lightweight features, the ones that would consume less, let's say, required less computations, so they wouldn't create a huge overhead over our method. And the second reason was that we have used feature selection methods, and they have indicated that a combination of those features could result into a very accurate, let's say, prediction of our QPs. I'm also giving here an example of the content dependency of the crossover 4K QP over the standard deviation of the temporal coherence. And as you can see there, it looks like there is a linear correlation between those two features. I don't know if you noticed, but in the list of features, I have also included the predicted crossover QPs. For our work, we do a sequential prediction of these crossover QPs. And for each, starting from the higher resolution, so starting from the 4K here, and as we go down the resolutions, we use the previous predicted QPs. And because, as we explained before, there is an underlying relation between the crossover QPs, an underlying linear relation. This can act as a feature and help us better, let's say, predict the next crossover QPs. So for this specific data set, which has these SI and TI distributions of characteristics, as you can see, the average value is around this area, and the average TI is around here, which also means that we are expecting deviations for sequences that are outside the 95% of that distribution. And this is actually acceptable because it is quite, those sequences are quite representative of the content that we can find out there. So some more technical details before I start showing the results. As I said, I'm showing the results from this paper. We have used HUVC and the latest reference software 16.20 to do that. For the spatial down and up sampling, we have used the Lanczos 3 filter from FFmpeg. And we compared our method against two state-of-the-art solutions, the brute force method, which is also the ground truth, the method that produces the ground truth, that does the exhaustive encoding with a QP step of 1. And then we compared against an interpolation-based method by using 7 encodes per resolution, and then using interpolation method to fit the curve. And this, of course, as I said before, results into a suboptimal convex hull, but it can provide a good approximation of it while significantly reducing the number of pre-encodes required. Okay. As I said, we have applied feature selection methods, and we have applied, in this case, the recursive feature elimination in order to be able, let's say, to determine the smallest set of combined features. We have also done some manual feature selection just to make sure that it works, because, as I said, I have been working those features a long time, so I kind of know what to expect as well. We performed the sequential prediction of the QPs, starting with a high resolution. And then we have tested various regression methods, such as SVMs with different kernels, random forest, but Gaussian processes were in this case the best performing models. And to avoid overfitting, we performed a 10-fold cross-validation. So the results I'm showing are after the 10-fold cross-validation on this 100 sequences. So in figure 14, 15, and 16, you can see the predicted crossover, 3 of the 4 predicted crossover QPs. And in table 5 are the results on these predictions. As you can see, the numbers are quite high, so R squared is quite high. But again, we do have a deviation of about 1.5 in absolute error for the 4K, which is the first QP that is predicted. But as you can see, going actually in lower resolutions, because we are using the previous predictions, we are able to provide a bit more accurate predictions as well. This, of course, has also to do with the range of QPs that are to be predicted, because as I said before, we had also a cap on the specific problem formulation. We assumed that 35 was the highest QP. So these results show the BD rate and BD PSNR histograms of the proposed method against the interpolation-based method and against the brute force method. The reason you can see a more, let's say, large bell on the interpolation, the proposed against the interpolation-based method, is because the interpolation-based method itself against the brute force, which is the ground truth, has quite a deviation in some cases because of the approximation errors that result by using the only 7 QPs in order to fit the rate distortion curve per resolution. And a few results over here that show the predicted convex hulls using on the campfire sequence, which is quite known, and on the dinner sequence from a dinner scene from Netflix. And as you can see, in the first case, we have a very accurate prediction of the convex hull. In the second case, there is a good prediction. There is a slight deviation But that is also because of this spatial shape that the convex hull has, which is not, let's say, which is a bit further from the standard shapes that you can see in the ray distortion curves. So this is a result from the tails of the distributions I showed earlier. Now, a few words on the complexity of our method and how much overhead our features extraction brings over this method is that I have computed the time that requires to extract the features, the spatiotemporal features required for the prediction from the native resolution from the 4K sequence, and I have compared it against the encoding time for the sequence at QP27, which is usually quite high, and the feature extraction is about 18% of that one encode. So I would say that compared to all the encodes we have to do, usually the cost is not that high. And then if we think about the number of encodes required in order to extract the convex hull and build a bitrate ladder by using the brute force method or the interpolation-based method against the proposed method, we can see that we have a significant reduction of required computations by following our method. So to recap, we have proposed a method that can predict the crossover QPs, and based on that, then we can estimate the bitrate ladders of the considered resolutions based solely on spatiotemporal features extracted from uncompressed content at their native resolution. And we only need a small number of encodes then to clearly define the bitrate ladder. The first results, as you have seen, they look quite promising. And we hope that with the next results we are going to share with you in a few months with an extended set of resolutions and the extended method I have presented, we are going to achieve very similar results to that. So for our future, our work, of course, will be to finalize this framework. And we have been thinking also about testing our method with other codecs, but also to see whether this method could somehow be reworked in order not only to identify the cross-codec optimizations of not only each codec bit rate ladder, but if we're able, for example, to estimate what the bitrate ladder, this content-gnostic bitrate ladder would look like in different codecs across different codecs. So that's a very interesting project for me that I have already started work on. So here are some of the references that I have referenced through the slides, and you can all find online. And yeah, I hope to share with you very soon the other paper. So I would like to thank Leverhulme Trust for funding me for the past 3 years with a personal fellowship. I would like to thank Netflix and Joel Sol and Mariana Afonso for supporting me with this work, and of course VA Lab and Professor David Bull for hosting me as a postdoc for the past 5 years in Bristol. And of course NVIDIA, the seeding grant from NVIDIA that have provided us with GPUs to help our work. And a last note, as you have seen my background, my backdrop, we are organizing in 2021 the Picture Coding Symposium in Bristol. So for those who don't know about it, I would like to invite you to submit your work in our conference. And since we're still considering the scenario of having a physical event, So I hope to see you all soon here in Bristol. Thank you.
Thank you, Angeliki, for the nice talk.